natural next step then so a natural next step then is to say, well, what about having more than one step in between, right? So we are looking at this single step between them. We could have two steps where we're taking the reward and then the reward at the next step and the following step discounted appropriately and then using the value function, or having n of them arbitrarily, this many, and counting those rewards, and then at the end having y gamma to the n with our value function filling on after that. Right, so these are kind of natural things to try to do. And so in order to do that, we're going to have this introduce some new notations, and I'll go through a couple of different versions because some of them are easier to understand than others. The ones from the textbook, they'll use this delta v a fair bit to define the backup. And so remember, if we go back to our main equation, right, which we'll have a lot of times, we have our return at a particular moment minus the value that we're going to have at this time step. Right, so we're taking this difference between the reward we actually received over n time steps and subtracting it from our value, which was our expectation, and then talking about and learning from that. So kind of in general, depending on how many steps you're doing here. So I guess, yeah, that's why they're using this notation, right? So in our TD version, we're always talking about, or in SARSA or in value iteration, right, it's small r plus one step, right? But if we talk about this definition that there's a two-step return and here's the n-step return, r to the n sub t means we're taking the rewards out over that many steps into the future and discounted properly, and then we take the value function after that, right? So if that's what it is, then TD kind of n steps ahead is just defined this way, right? And we're saying it's like that, and when we say it's delta, essentially, right, what we're doing is that we're saying this is like plus equals delta st, right? Right, this would be the update after, right? Because what we're really doing is saying that we're taking the current version st, and then we're adding alpha, and then r, and all that stuff, right? So it's really kind of like plus equals, or they're just defining this difference to be the part you're going to change. So there are some convergence properties of this, showing that an n-step method will converge at least as well as a single-step method, because you're not throwing away any extra information, right? So for the single-step return, right, you look at the next step, you follow your action, you maximize the state you would end up in by basically saying pick the maximum action, and so what state would you want to be in? Even in the best case scenario, where this is the best state you could end up in, the difference between what you're going to get for your expected return and what your policy, your value function on the policy gives you. So, right, so v here is kind of the value function that really represents that state, and expectation over pi here is you using this return to produce this expectation. And so that difference is going to be no bigger than the one you would get from a single step. So we already had proofs reference that this converges, so this is also going to converge. You're going to be better off, and at worst, it'll be the same. Okay, so there's a couple slides on how this kind of works exactly. Just to give you an example, but then you're going to see it much more clearly in your assignment with doing this for SARSA. But we'll go through that algorithm directly. So you can think about a very simple MDP. We've got a start state C that you start in, and you can go, no matter what action, you can go left or right, but you don't get any rewards. These labels are rewards, and the end states are these squares at the ends, and that's where the terminal states are. But you only get a reward if you go off the terminal state onto the right, right? And so this is a hard thing to explore, and I think we showed this before with TD learning, because initially you don't know what to do, and you don't get any feedback until you get to the end, and that feedback has to go through backups to get to the point of you learning it. Right, so how would these look-ahead step things work here? So they did experiments with this very simple domain and ran simulations, just having a random walk kind of through this and having some policy that tries to optimize it, right? And so what are we looking at here? The number of steps happening. Alpha is the learning rate, right? So as the learning rate increases, that means you learn more from surprising results. And so you more quickly learn, but you often overlearn and get stuck in a local minima, right? So this one where it's very aggressive in one step gets here. The numbers on the lines are the ends. That's why they line up in multiple places, right? So if you're looking 8 steps ahead or 5 steps ahead, you're kind of even with a very low learning rate, your error goes down, but then it goes up again. If you increase the learning rate and kind of overdo it, you'd kind of fixate on something really bad. So you'd have to have this learning rate tuned. So we would usually say in this domain, this is kind of the best because it's kind of giving you the longest area of learning rates that are kind of plausible. And it makes sense, right? Because there's about 3 steps until there. So if you're looking ahead 3 steps, that should be the most efficient way to learn this. You can basically remember 3 steps back when you're updating things. That's kind of what's happening, right? And then this is offline versus online, right? So we can see how the graphs get compressed inwards, right? And so if it's offline, that means you're doing Q-learning versus SARSA, right? So if you find a way to implement this with Q-learning or SARSA, with offline, you can do better with a smaller learning rate, but you have to kind of explore around more, and it takes risks. Remember, it's the one that walks towards the cliff rather than the one that stays away from it. But they're essentially the same shape. It's just a matter of parameters, and this is one of the unfortunate things that will often happen, right? You've got a bunch of parameters like alpha and gamma, and tuning them in the right way is what gives you this feasible space of when you can, when it will perform well. And a lot of the research in reinforcement learning is trying to find ways to understand these parameters better and reduce the assumptions that are needed for them, and do experiments with them. But today we're actually going to introduce more parameters, so we are not helping the situation. So why are we doing this? The hope is this is going to make it more efficient for us to do a better policy with less computational tricks and not having to store all the returns and rewards for all these steps. So the first step to getting that is realizing that we don't need to store all of the rewards, the returns of all these different levels, but because you can average them together, right? So we talk about the average return over some policy, over some period of steps. We can create backups that say, here's a return 2 steps ahead, and here's a return 4 steps ahead, right? That's what we're doing there, and then we're basically giving us that. And we can combine those together, right? And that would just give us this other average return, which takes those 2 and gives us a new one, right? It's totally fair to do that. And the rewards added up over time and scaled by a gamma would still be in the right kind of scale if we do this. So that's a kind of very specific idea. And if you want to generalize it fully, this is where we get TD lambda, right? So this lambda character, it's a Greek letter, and if you were doing your LaTeX, it's lambda. we basically do that idea where we say, let's come up with a weighting so that every number of returns, all the way up to some end state, till we get to the end of the terminal state of this MDP where we decide to stop, that we're going to average them and weight them up, so that the idea is that the sum of all of these different components is going to sum to 1, right? So we come up with a number lambda, which is going to be in the range 0, 1. Often it'd be something like 0.9, just like gamma, but it means something very different, right? Because here we're saying take the one-step return, right? So this is TD0 that we've done already. This is the SARSA that we're already using, and we're going to give it a weight of 0.1, say, if we're using 0.9, right? And then for the second one, we're going to give it 90% of 0.1, right, for the two-step return, right? So we're going to get that. And so we'll get something slightly smaller, 0.09. And then for this three-step return, we'll get 0.81, because we'll say take the 1 minus lambda and times, I mean, really we're saying in the way the formula is going to work out, it's 1 minus lambda times lambda times lambda, right? Because each time we're going to combine that in there. And we'll keep making it smaller. So it gets smaller by 90% every time. That essentially the longer and longer ones, we're not going to be weighting them as much, but we're still going to use them, right? And again, this is how far forward we're looking, right? So we're currently here trying to update the value we're at ST, and we want to update the value of VST. And we're trying to say, well, as we go forward, how far back should we update this thing? And that will give us this new updated delta V, which will be somehow this scaled weighted version by lambda of the returns and the differences between our expectations. So we use this general form here to say that, yeah, the immediate one gives us 1 minus lambda weight, and then we kind of scale it out. And the idea is that this formulation is just chosen so that it's the shortest one is correct, is the heaviest weighted, just like T0, but that we're going to basically scale it smoothly off into the future, and that they all add up to 1. So we're distributing the importance of the return calculations to these different lengths, right? So this is more of a graphical way of looking at it, that we start off with the highest one here and it goes off, and the area under this is 1. And we have to have an exemption essentially to say that at the very end, whatever's left, we have to say we're going to basically split the difference. So whenever we stop at t, we've got to come up with the remaining lambda that fills this space, right? So this one will have a special value. And so the way we actually would write it out would be like this, like the one we had before, where it's just for every step, we're kind of running forward. Once we get that return, we're going to weight it in a smaller amount. And then when we finish our MDP and stop or hit a terminal state, the lambda will be larger than it would have been, because it has to basically make all this add to 1, right? Because having the lambda sum to 1 is critical to say we're not changing anything in the sense of it. So once we have this weightings approach, we get this property that we say we wanted, where we can smoothly vary between Monte Carlo and TD0, where this formula, if you put in lambda equals 1, you essentially get Monte Carlo, and that's because this part ends up being 0, and so this all crosses out, and that's just 1, and so you just get the return at the end, right? So your return is the return for that time step, basically how many time steps ahead it was. And for lambda equals 0, this becomes 1, this gets crossed out, and this becomes 1 only in the case for the first one, where n equals 1, and in the other cases it's 0. And so you just get your one-step return, which, in our one-step return is that RT plus gamma VST, right? Have that right, yes. Right, so that's our idea, and this is kind of this idea that we're looking forward. We have a nice weighting scheme using lambda all the way that says, well, let's integrate knowledge from longer views into the future and help it update us. And that, as we've seen from the plots on the simple diagrams, this will improve our chances at converging, right? And so they have a new version where now instead of saying how many steps forward you go, it's what the weight of lambda is, right? If lambda is really small, then that means you basically don't use long ones at all, right? You just say, it's like saying TD0 or TD1. And as you let lambda go up, you start getting closer to that system where it uses the nearby, the shorter ones, so it'll use the one-step difference, the two-step difference, the three-step difference, and it'll scale away very quickly. If you really want to keep all of them, you can, but it's basically gives you Monte Carlo. So it makes it a bit easier rather than just picking 3 or 7 based on the size of your MDP. Lambda 0.9 actually works in a lot of cases, and then it's one more parameter, but it's a parameter that has a meaning that it scales independently of the state size and everything. So it's actually helpful way to think about it. Of course, how do we actually compute this, right? Understanding it going forward is kind of very easy to see, but if we want to actually implement it, we'd have to keep track of all the rewards we're getting at every time and compute the returns by summing them together, right? We need to have these returns, all of these ones, basically storing them and then just weighting them down and keep using them, right? Because when we get here, we're going to have to copy it back to all previous times using the reward we got here to compute returns to update the values of st and st plus 1. So it seems a very inefficient way of doing this. Luckily, someone came up with a trick for doing it in the reverse way, but it means we have to introduce a few more Greek letters. We're not going to quite use up the entire alphabet yet, but we're getting closer. So this will be the backward view of TD lambda.